Everybody, welcome back to another weekly tech tip here at 45 Drives. So today's video is geared towards demystifying benchmarking and specifically benchmarking for your use case or your workload. So with that being said, let's jump into it. All right, guys, before we get started, I definitely recommend watching Tom's video over at Lawrence Systems because he does a great intro into file and how it all works. He also talks about IOPS versus throughput and does a great job showing different ways to benchmark. Today, however, I want to go a little deeper on benchmarking specifically for your workloads. So one thing I really also wanted to touch on in the beginning is something that Tom touched on as well, and that is in a vacuum, when you have nothing to compare it to, benchmark really doesn't mean all that much. While it's fun to try to get to the biggest number you can, it necessarily isn't really that helpful when you're trying to understand how your drives are going to perform in very specific workloads. So it's very easy to skew your benchmarks in order to make your numbers look a certain way if you have a specific goal in mind. So also, as Tom touched on, marketing just really loves to take those really big numbers and shouting them from the rooftops. So one thing you'll notice, however, is 45 Drives doesn't really have a ton of published benchmarks that we parade around like some other vendors might. Our philosophy has really always been geared towards benchmarking for workloads specifically and workload applications as we get more familiar with our customers' use cases. But that being said, as a storage vendor like us, there is a real tangible benefit to taking the dyno approach, so to speak, where you put your car on the dyno and push it to its limits. So what that ends up looking like for us is benchmarking our servers without file systems or RAID arrays, and really getting to the core of what our servers are capable of pushing when all the disks are maxed at 100% with as few bottlenecks as possible. We will be actually publishing some really great stuff showing these type of numbers, so look out for that in the future. So while these numbers certainly have their place, they may not be what is most important to you depending on your workload. And that is exactly what I want to explore in this specific video. So let's look at why benchmarking storage seems really simple from the outside, but then when you start digging, things get really complex really quickly. So starting at the disk level is great and all, but that's not really how we use our storage. There are many layers that come into play before we actually get to put the data on the storage itself. So every time you add another layer, you're further complicating the chain. So for single servers, for example, you can think as adding your ZFS array and everything that comes with it, such as your redundancy profile like RAID Z1, RAID Z2, your VDEV configuration, your record size. Then you have how the data will actually be accessed by clients. Is it over the network? And if it is, should we be doing our benchmarks over the network? So finally, we get to our actual workload. So what type of I/O pattern does it follow? Is it sequential or is it random? Is it mostly reads or writes? What block size does your workload favor? Does it have a favorable I/O pattern that we can queue up for a good number of I/O? Or is the queue depth very low where you can't have that queued up? And then for Ceph, it gets even more problematic because you have client access via RBD for block, you've got ZFS for file system, you've got RGW for object, and then you've also got replication versus erasure coding for your pool types. And all of these things have different performance characteristics. However, don't lose hope yet. Today, what I really want to do is try to demystify this black magic we call benchmarking and try to help you learn how to benchmark for your workload instead of just trying to get that biggest, most impressive number you can that might not necessarily mean anything when it comes to your end use case. So the end result might not only help you get a better understanding of your workload, but it can also help you better prepare your storage array for that workload. So you can actually end up with a better built and better configured Z-pool or storage array in general. So let's get started. All right, so for the demo here, as you can see, I have an agenda laid out for us. At first glance, it definitely seems quite daunting. There's a lot of stuff here, but if you're interested in this stuff, there's going to be a lot of really good information here. So I recommend, if this is something you really want to know, like benchmarking for your workload or understanding how ZFS works to help you build your ZFS pool better for your workload, there's going to be a lot of really good information here. However, if there's only certain things that you might be interested in this kind of agenda here, what I'll do is I'll leave timestamps down below as to every little part of it, so if you want, you can skip around to different parts of the demo. So without further ado, let's get started, and I want to go through the entire agenda here and kind of so you are prepared and you know what it's going to entail. So to start, I guess the format or the name of this is really benchmarking for your workload to help you inform your decision on the best ZFS configuration you need. So when I started this, I really thought it should be benchmarking for your workload, but as I really started thinking more and more, I realized just benchmarking for your workload with ZFS is one thing, but really understanding how ZFS works underneath to help you and guide you to the best type of pool that you can have for your performance needs is also very, very important. So both of those are really intertwined. So first we'll start with talking about storage array caching, read and write, and whether it's proper to actually disable that for benchmarking. There's a little bit of a debate around that, but spoiler alert, for us, we recommend taking both into account, especially depending on your use case. There's going to be lots of reasons for that, and we'll get into that. So I'm going to talk about ARC and L2 ARC and ZIL and SLOGs and whatever they are, because they sound pretty crazy at first glance, but we'll get into detail about what ZFS is and how it uses those. I have a link here which has some really good diagrams I'm going to show when I talk about that to help drive that home. Then we're going to jump into synchronous or unbuffered writes versus asynchronous writes or buffered writes. We'll talk about the fsync call when doing FIO benchmarking, and we'll talk about IO or queue depth and how they affect performance during these benchmarks. So we'll run a benchmark that is just essentially a unbuffered random write to our array, buffered write, so asynchronous writes to our array. We'll show that the performance is great. Then we'll jump in and we'll do a unbuffered write, which actually has to go directly into the array before the acknowledgement, and you'll see the drastic difference in performance there. And then we'll look at queue depth and how that can affect that as well. Then what we'll do is we'll add a slog or a ZFS intent log that is separate from the one that's normally on the pool on a SSD to show how that can actually drastically increase your unbuffered write performance. Yeah, so then after we add that slog or that separate ZFS intent log, we'll rerun the synchronous write test and see just how much of a performance benefit we see by moving that off of the Z pool and putting on a dedicated SSD drive. And then I'll explain why kind of that happens and what exactly is going on under the hood here. Then we'll take a look at some example workloads that you may have in your environment and what and how they use storage. So we'll look at like virtual machines and databases, which are typically the synchronous type workloads. Then we'll look at things like video editing or backups, specifically Veeam, because I love Veeam. I've done a lot of work with Veeam. So we'll look at how they actually commit writes, which, spoiler alert, they are more of the asynchronous type. And then we'll go into read caching and kind of how that plays into ZFS, because it is very, very hard to benchmark ZFS without ARC having an effect. And we'll explain why that is, and then we'll explain how you can kind of get around benchmarking without the ARC. But because ARC is such a core feature or a core part of ZFS, what you should really do is benchmark with ARC and take it into account to your data set and try to understand your workload and how large your active data set is, and then try to build your ARC around that so you're never exceeding or very rarely exceeding your ARC on your active workload. So we'll talk about that, and then I'm going to show you some really cool benchmark that I actually ran prior to coming here because it takes a while to run this one, and we'll show you the results and show you kind of how that ends up. Then we'll get into the end here and we'll talk about the best configuration settings for your storage to maximize performance for your workloads. So we'll take your understanding of how these workloads read and write that we've talked about up until this point, and then we'll design your storage pool around it. So things like the best RAID profile for a given workload. So things like mirrored VDEVs for random IO or RAID Z for sequential type workloads. The best block size for a given workload. So this one is very important, and we'll show that with some benchmarks as well. So we'll find the block size of your workload, which is very, very important. So for example, databases many times use 16 kilobyte block sizes. Veeam backups can vary depending on how your backups are set up, or if you have NAS-based or direct attached storage-based backups and things like that, but you still can find that. And then the cool thing is with ZFS especially, is you can have your data set match that block size to really give you a boost in performance. And we're going to run some benchmarks to show just how much that can help. And the really cool thing about ZFS is since you can have multiple data sets with different record or block sizes, you can have all these different workloads with different performance characteristics for your needs, which is really, really cool. And then we're gonna wrap it up by just talking about sizing your arc and your L2 arc and your slog for your given workload. And then the very, very last thing, this is actually one I want to put to you guys in the community because it's one that I personally don't have a whole lot of experience with. It's one of the newer features of ZFS, but that's a special VDEV. And what it does is it allows you to offload your metadata to a special VDEV. So like you could have like NVMe high performance. And from what I've seen, and like I've done some work with it, but nowhere near as much as I've done with the rest of ZFS. So I'd love to hear if anyone has any experience with it and what their experience is. Is it great? Has it helped? Has it not helped? But I imagine if you have a very, very dense ZFS file system with lots of files, it could be a pretty big game changer. So yeah, with that being said, that's the agenda, and let's actually just jump into it now. All right, so let's talk about read and write caching and how that works with ZFS. So first, let's take a look at this link here so we can talk. So to start, the way that ZFS writes is, like I alluded to, you have asynchronous writes for most workloads, like things like, if you have a Samba share, if you're just writing, video files, or if regular file sharing, things like that. Anything like that is typically done with asynchronous writes. And how that works is the client will contact the storage array and it will have a bunch of writes ready to go, and essentially they'll go right into RAM on the ZFS pool, and immediately the client is okay with that, and it'll keep giving more and more writes. So the ZFS pool can continuously buffering those writes into RAM and then flushing them into the Z pool in transactions, because ZFS is a transactional file system. Now that's great because it allows the client to just keep giving write requests as fast as it can until the RAM or the Z pool slows down. So a lot of times, if you got small bursty writes and things like that, it can happen very, very quickly, and the client sees it as a very, very fast performing array. Now, asynchronous writes are very different than this, because what they do is, while they do still go into RAM, these type of workloads are very important that the data gets flushed actually to the long-term storage before a commit happens, or before an acknowledgement happens. This is very common for databases and for VMs especially. So if you do hypervisors and things like that and you're running virtual machines, it's very typically all sync writes. And the reason why they do that is because, if, for example, with an async write, for example, if you lost power to your array, it could be that when it comes back on, you could potentially have some data loss. And with these type of workloads like databases, that's not acceptable, right? And so what happens with ZFS is that sync write goes to a ZFS intent log, which is where the write first gets committed. Now, when that first gets committed, then it's able to go back to the client and say, it's written, it's at least been in the ZFS intent log, you can keep going, here's your acknowledgement. And so by default in a ZFS pool, especially if it's all spinning storage, that is located on the same disks that has the actual data, where it also will be committed after it goes to the ZFS intent log. So what you end up with for a sync write, if you don't have a separate ZFS intent log, is a double write penalty. So you get the ZFS intent commit, and then you also get another write to the actual pool where the final write gets committed. And so that is not great for performance. So believe it or not, if you take a separate device, it could even be a spinning device, and you put a separate ZFS intent log on that, you will actually see performance benefits because it removes that double write penalty. We wouldn't really recommend using a spinning disk for this, because it's best, if you're going to do a separate ZFS intent log, put it on some very fast flash. But it causes it not have to do that double write penalty on the same disks that are doing all the actual writes. So when we have workloads like virtual machines databases, we definitely recommend, if you can, have a high performance cache of NVMe or SSD, typically in a mirrored array, because you need some safety there as well, and put the ZIL on that, the separate intent log on that, and you will see a good performance benefit to that. And we're going to show that right now, actually. I will be talking about the L2 arc and the arc as well, but let's stop there and let's do some benchmarks and see how this works. So we have our Z pool here set up, and let's take a look at it. If we do a Z pool status, we can see we have a RAID Z2 with a number of spinning disks here. Okay, that's great. So let's pop back to our agenda here and let's look at our tests that we're going to run. So the first one we're going to run here is a random write test. We're using the POSIX AIO engine. There's lots of engines that FIO has, but I like this one for Linux for file systems. We're doing a random write. We're using a block size of 4K. We are not using the fsync flag, and it's 4 gigabytes in size, a single job, and a single queue depth. And we're going to run just for 60 seconds. So this is going to be your asynchronous type workload. So regular workloads where it doesn't have to get that acknowledgement and it can go much, much quicker. So let's run that right now and see what we get. Here we go. We got our test results back, and we can see here we have an IOPS number of 344 and a bandwidth of 1,377 kilobytes a second. So that is with the asynchronous writes that we talked about, and just to rehash on that, that's this write comes into RAM and then the client is okay with it and will continue writing to it. It doesn't have that ZFS intent log penalty. It actually doesn't write to the ZIL at all in the async type of writes. Okay, so we ran that. Now let's switch it up and let's make sure that every single write has to be synced prior to the next one beginning. So we're going to run the exact same benchmark, but this time we're going to use fsync equals 1. And so this is going to be with the double write penalty. Okay, so we got our test numbers back, and we can see we have a considerably slower performance here. So we dropped all the way from 344 IOPS all the way down to 86, and our bandwidth is only 344 kilobytes. Now, I want to say in the beginning as well, even that first number obviously is not anything fantastic, but you have to remember this is a spinning disk array, and it's using RAID Z2, not any mirrored VDEVs or RAID 10s, which is what you would want for high IOPS, especially of random IOPS. But we will get to that as we move on. But we can see here now, so with that double write penalty, we were considerably slower. So now let's throw a SSD SLOG in the mix and let's see how that performance changes. So we'll go back to our agenda here. So we ran our buffered and our unbuffered writes. Well, we could also do one with a queue depth, but I think maybe I'll skip that for now because that is really interesting. Just quickly to talk about why I have that here. So the really cool thing is if you're having the synchronous write, what's happening here is with the single queue depth, that means only one 4K write gets sent and then it gets committed. Where if you have a high IO depth workload, what happens is the client can actually send, in this case, 32 of those 4Ks all at once, and then they can be committed transactionally all at the same time. So you will actually see a benefit, even without a slog, if your workload has a higher IO depth, because it ends up a little more sequentially because it can take all those 4K writes, 32 of them in this instance, and write them all at the same time rather than have to write one, commit, go back, write another, commit, go back, etc. So you get that. Okay, but moving on. So what we want to do is we want to take our Z pool and we want to add a separate ZFS intent log to it. And so let's go back. So let's list our block devices here. I have quite a few SSDs, but I believe SDP, is an SSD here. So that will work. I'm just going to copy and paste this, and this will add a separate intent log to that array. So here we go. Now if we do another Z pool status, we can see we have our RAID Z2, but then we have our slog here. Very quickly, I would not recommend a single disk for a separate intent log because that is very important not to lose the data on it. So a mirror is much more important. Okay, so now that we have it done, let's rerun our test again and let's see exactly what we get now. Okay, so we're back. We've run the test. So let's take a look here. This time we have 540 IOPS and we have just over 2 megabytes, so 2163 kilobytes a second. So that is considerably faster than having your ZFS intent log contained on the same Z pool. So as you can see, that single SSD has improved this workload considerably. So what is that telling us? Well, what that's telling us is if we have a workload that requires the use of synchronous or writes, that we should definitely consider looking at a separate ZFS intent log for that array, especially if we need to use spinning disks for our array. SSDs, you can get away with a lot more, obviously, because they have a lot more random I/O performance than spinning disks will. But if you can't, and the great part about this too is ZFS intent log does not have to be a very massive SSD. You can get away with some of the smallest SSDs, which is totally fine. So okay, so we got through that, and we now see, and we have some great conclusions here about sync writes and what can improve that. Now, again, we haven't gone into depth on like different types of arrays yet, but what we can see is RAID Z2 is not fantastic for any type of random I/O to begin with. So you might want to also benchmark at the same time in this stage before you actually put your workload in production. Take your disks and benchmark them in a few different configurations for your workload. So mirrored VDEVs, or RAID 10 is what you would call it in traditional RAID, is definitely the best way to go for getting the highest amount of random IOPS as you can. Believe it or not, a RAID Z2 or a RAID 6 in this instance actually only ends up with, when you're right at the disk level without any caching or anything helping, you only get the IOPS of a single disk in this configuration, random IOPS, I should say, of a single disk in that configuration. And that's why these are very, very small numbers that we're getting, right? So definitely try, mess around with the different types of RAID arrays while you're doing this testing, and you can really get to understand the best array types for your workload. Okay, so let's move on. So now we're going to look at example workloads, and really I'm just going to talk about this quickly, and we'll move past it and we'll get into some other things as well. We're going to talk about example workloads and how they use storage. So we already kind of mentioned that, like virtual machines databases are really based towards, like we said, sync writes, video editing, backups, standard day-to-day stuff. You're really going to be using async, like anything on a file system level. If you're just using it as like a shared drive or things like that, you really have nothing to worry about there. You're going to be able to take advantage of that asynchronous write. Okay, so what about read caching now? And this one is actually really interesting when it comes to ZFS specifically, and that's because ARC, or the adaptive replacement cache, which is a read cache in ZFS, is so core to what ZFS is. So when I say that, what I mean is like a traditional file system, other file systems, what they will normally use is your operating system's page cache to cache writes and reads and things like that. Whereas ZFS has its own adaptive replacement cache with a much different algorithm and a different way that it works than just a regular file system. So let's get a look at this link and I can talk more about it. All right, so here we have a traditional cache and file system and how that normally works. It's called least recently used caching. And so what it ends up being is the most recent data that comes into that cache goes to the front of the line, and anything that can't remain in here, the oldest stuff, is going to get kicked out, and it's just going to continue on that cycle all the time. That's fine for some workloads, but ZFS has something much, much better, especially for things that aren't just a standard file system. Like if you've got a lot of different workloads running on a ZFS array, which you definitely can because it's built for that type of workloads, the ARC algorithm is going to benefit you considerably more. So it uses much better algorithm. So it not only uses the least recently used, but it also uses a most frequently used, which is more important. So as you have a piece of data or some data in your data set that gets used more often, it gets a higher weight within your adaptive cache as time goes on. And so what you can end up with, particularly with ZFS, you can have a very, very large adaptive replacement cache. You can have 256 gigabytes of RAM dedicated just to your ARC, which can allow for a lot of your active data set to remain cached and be ready to be accessed for your workloads very, very often. So when people say, you should get rid of your cache when you're doing benchmarks, it's not real world. Well, in this case, it kind of is. And then not only that, it's actually really hard to benchmark ZFS and have ARC not play a part or not actually affect your results. There are some ways, and I'll show that. But really, what I would say is benchmark with the adaptive replacement cache in mind, but also keep in mind the size of your data set and try using that large of a data set on your benchmarks. It might take a lot longer. So like if you actively use, upwards of 156 gigabytes a day between all the different users that are using it, you can benchmark using that large of a data set. It might take a lot longer, but you can get more real world statistics that way. So that being said, so that's really all I just wanted to get to is ARC is very different than standard file system cache, and it plays a much more central role to ZFS as a whole. And so that's why we like to benchmark our our read performance with the adaptive replacement cache in mind, but also keeping in mind that if your workload does move outside of that adaptive replacement cache, things will degrade, performance will degrade. And so the idea is when you're building for your workload, try to get your ARC size correctly. And if you have to, you can put an L2 ARC in as well, which is a layer 2 ARC using more traditional flash or NVMe. But my recommendation would be first go with as much possible RAM as you can, and only at that point when you can't go anymore, then start looking at an L2 ARC. Okay, so that being said, let's head back to our agenda here. So yeah, let's talk about the options. So like I said, testing with that exceed your ARC, which can help you. So when I said that benchmarking ZFS and having the ARC not play a part is really hard. So in file, for example, you have a direct flag that you can turn on that's supposed to bypass cache completely. For the longest time, ZFS actually didn't even support that. It does now. But you will see, because ARC is just so core to how ZFS works, you turn that flag on, the performance is not going to be different. If you have it on or off and you run a benchmark on file, you're still going to see read caching from the ARC play a part. The way that I've been able to really show the results of worst case scenario with the ARC failing at this point is benchmarking with a massive data set. And so just by example, I have one here. It took a really long time, so I'm not going to run it here, but let's take a look at this result here. So we can see I ran a random read benchmark on the same array using just a 4 gigabyte data set size. And we see some incredible IOPS, right? This is spinning disk storage here, but we're getting 24,000 IOPS, which doesn't normally compute, right? But that's because the ARC is doing its job and it's caching a lot of that data set. Now, what I did then to try to trick the ARC or try to bypass the ARC was the first thing I did was I put a whole lot of garbage data onto the array very quickly. So flushed it with a whole lot of just data that moved some of the data out. And then from there, what I did is ran another benchmark with a very, very large data set of 100 gigabytes. Now we can see those read IOPS very, very quickly dropped very, very low. We went from 20-some thousand to 189. Now again, that is a result of the fact that these are random read IOPS, and when you're getting to the disk level, we're using spinning disks in a random IOP best scenario, and that's why we see it drop off just so significantly. But it is important to know these things, because you could not know it and build a Z pool that with a RAID Z1 or 2 needing random IOPS and not understanding why you're getting such poor performance. And this just shows exactly what happens when your ARC is no longer able to help you. And so, yeah, so let's continue on. And again, I would recommend, if you are going to do these benchmarks for your workloads again, try some different Z-pool configurations. Run the same test again, try to bypass that ARC, but this time maybe let's have a bunch of mirrored VDEVs for your spinning storage, and you will get considerably more IOPS than this. Remember I said in a RAID Z2, you're only going to end up with about the random performance of a single drive. Well, that 189 IOPS pretty much covers it. Obviously there's a little bit of extra overhead. A spinning disk can usually do between 250 to 500, so we're pretty much on the money here. All right, so let's move on. So now let's talk about the best configuration settings for your storage to maximize your performance for your workloads. Because I did a lot of talking about ZFS and how it works and benchmarking to show you how it all works under the hood, but we haven't really gotten to the point of best benchmarking for your workload. So one of the really good ones that I would recommend, like I've talked about already a few times, is figuring out the RAID profile best for your workload. So find out if your workload is sequential or random. So if you're doing video editing, a lot of time that's very, very sequential. Sometimes you'll get some random if you're scrubbing through your timeline very quickly and things like that. So you need to be able to kind of have some sequential performance and some random, but that's great. That's where the ARC comes in. It gives you the ability to scrub through that timeline with a lot of it being in your ARC, in your cache, and be able to put up and handle that. But here's one that I really, really want to show off, and we're going to do some benchmarks to show this off. So let's look at the best block size for your given workload and find out what the block size of your workload is. So I talked about it a little bit earlier, but let's show this off. So many of our databases use 16K, like I said, but if you have a certain database that may use a different size, find that out. That's definitely going to be able to be something you can find on the internet. Again, Veeam backups can vary. Video streaming is a little differently. So again, if you're streaming video or editing video, you might want to go with some larger block sizes or data set sizes, record sizes, sorry. I wouldn't go like 1 meg or 4 meg like you might see in some benchmarks. So if you've ever done benchmarks yourself or seen other people, sometimes you'll see people benchmark 1 meg block size or even 4 meg block size, which is really cool. You're going to get very large streaming numbers, but there's really very few workloads that are actually going to work that way, where they're streaming large 4 meg blocks of data in and out. And for that reason, I think the largest I would ever recommend going for my record size on my ZFS dataset is like 512 kilobytes and see how that works. Because even if you do have very sequential needs, there's always going to be some type of random workloads in there somewhere throughout your workflow. Okay, so let's start. Let's create a new data set, and let's have the data set match the block size of our workload. So our workload in this instance is going to be 256 kilobytes. So we're going to create a new data set that matches that. So let's pop over to our Houston UI, and we're in our ZFS module here. So we have our SMB test ZFS pool, and we actually have a ZVol here, but we don't need to talk about that. So let's create a new data set or a new file system. We will call this 256K record, just because that's what it's going to be. Now we can add or remove things, but we're going to keep everything exactly the same to the parent pool except for the record size, because we want a good apples to apples comparison here. So let's go. We've got our 256 kilobyte record size for our data set here, and let's create it. Perfect. All right, so let's pop back into our terminal here. So first we're going to run this benchmark on the actual pool itself that's using the 128 kilobyte record size. So let's go and grab that benchmark. Here we go. So this again is running a random write performance benchmark with a block size of 256 kilobytes, and it's using a single job and a single I/O depth, and it's asynchronous, of course. All right, so let's run that right now. Okay, we got our numbers back, and let's take a look here. These are not any numbers to sneeze at, right? We've got 256K block size, and we've got 3,756 IOPS, and we've got a bandwidth of almost a full gigabyte, 939 megabytes here. Okay, that's great. So we did this on our 128 kilobyte record size data set. So let's pop into the one we just created. There we go. So we're in our new our new data set at SMB test / 256K record. And let's run that exact same test, and let's see what happens now where our block size and our record size match. Okay, so we got our numbers back here, and let's take a look. So we can see we've got a nice uplift in performance here of 4,521 IOPS, and we've now broken the 1 gigabyte barrier. We're at 1130. So what's different here? Absolutely nothing. The array, the Z pool, everything is the exact same. You're getting free performance here because you matched your record size to the workload that you're running, which is such an important thing. And you can say, well, my workloads are very mixed. I've got 10 different things that I'm using my Z pool for. Well, that's the amazing thing about ZFS is you just carve off a new data set. You can have one data set using this record size, one data set using another, and they're both getting different performance characteristics. So yeah, so that's that. All right, so we're almost ready to wrap it up here. We've gone through quite a lot. I don't want to drag this out too long. But before we wrap up, sizing your ARC and your L2 ARC and your SLOG for a given workload. So the ARC and the L2 ARC especially, what I would recommend is when you get an idea of how your workload is going to be used, what you're going to be doing with it, like I said earlier, I think the ARC is what you want to try to size as large as you possibly can before you go looking at an L2 ARC. A few reasons for that. One is because you're never going to see a performance benefit from an L2 ARC like you are going to see from increasing your ARC size. And secondly, adding an L2 ARC takes up some of the RAM space you could normally be using for your actual ARC. So you end up with less ARC and you end up with a slightly slower performing or quite a bit slower performing L2 ARC. So that's the big reason why I say max out your RAM first, then go looking for an L2 ARC next. For the SLOG, much simpler. You don't need a lot of data. Ceph, I'm so used to Ceph. ZFS is a transactional file system, and so the way it works is you're never going to have, you know, a terabyte of data sitting in your ZIL waiting to be flushed. You really only need, really at max, I mean, that's even pushing it, like 128 gigabyte NVMe SSD or SATA SSD. So, but what I would recommend is definitely going with mirrored ones at the very least to make sure that you have your redundancy in place there. And so yeah, that's that. If anyone has any other questions about workloads or what you're using your ZFS pool for or what you want to do with it, please leave them down below. We'll definitely answer. The last thing here though, so special VDEV and metadata. Like I said, I want to talk to you guys. I'm sure we have some ZFS aficionados out there. A special VDEV is really cool. It's fairly new, especially on like ZFS on Linux. While I've played with it and done some work with it, I think it's really cool and has some really big benefits. Like I said, it's nowhere near the depth that I've gone on the rest of what ZFS can do. So I'd love to hear your experiences. Have you seen a big benefit from that? And if so, how have you sized them? How have you built them? Things like that. So that would be awesome if you could do that. Okay, so that about concludes this demo. All right, and that just about concludes today's tech tip. Hopefully you enjoyed it. Before I finish up though, if anyone actually takes our suggestions here or some of our benchmarks that we run and try to tune your own workload, please, we'd love to hear it. Let us know what you tried, if it worked, if it maybe didn't help that much. We'd love to hear any and all feedback. Also, if this video gets 100 likes, I will do a follow-up video, but geared more towards Ceph clustering and maybe block storage and file system storage on Ceph specifically. So yeah, we threw down the gauntlet. If you get 100 likes, we'll do it. And then finally, I just have to shout out Tom Lawrence from Lawrence Systems again, because his channel is great. Love his content, always learning stuff from him. So if you like open source, you love Linux, definitely check him out because he does some really great stuff. And that being said, we'll see you on the next one.